Today I have the pleasure of speaking with Anish Verma. I met Anish earlier this year. He was organizing the 2021 Undergraduate Big Data Challenge through his role as the Chief Data Officer at STEM Fellowship. At STEM Fellowship, he leads the Data Science Division, directing the organization's data analytics to improve internal operations, and he oversees the organization of the National Big Data Challenge program, empowering youth to use data science in an interdisciplinary setting. I know that my team and I felt highly motivated to continue our research as a result of our participation and our mentorship from Anish. Anish is also a quantitative analyst for 1QBit, where he works to solve financial problems through quantum computing. From 2016 to 2019, Anish served as the executive editor and journal manager of the Science Undergraduate Research Journal at Simon Fraser University. He received his Bachelor's of Science in Chemical Physics from Simon Fraser in 2018 and continued to earn his Master's of Science in Theoretical Nuclear Physics from the University of Guelph a few months ago. In all of our past conversations, Anish has consistently led open and fun conversations with notoriously difficult concepts, and I truly can't wait to see what this conversation brings. Thanks for joining me today, Anish.
Thank you, Ben, so much for the introduction. I think you gave all the highlights of my life, so that's good.
Glad to hear. Yeah, I spent a little while on it, so I'm glad we gave you a good introduction there. So I guess generally speaking, I'd like to start off with a few just general research questions. So my first question for you would be, what made you get into research? What interests you about research? What's one of the most fascinating things that you've encountered with just research in general?
Sure. So why I got into research, right? So back when I was in high school, when I was trying to figure out what to do with my life, basically, right? I knew that, at the end of the day, what I wanted to do was one, make impact, a very, very broad and vague statement. And two, I wanted to understand at the most fundamental level, whatever I wanted to pursue, right? And to me, what that manifested as was scientific research. And truly, I don't think that a person is able to fully say that they have a mastery or understanding of a particular topic unless they try their hand at putting or pushing the bleeding edge of research further. So that's why I went into research at sort of an interest level. Now, I also want to note for your listeners that even if you're not super 100% keen on doing scientific research, I still recommend the experience because I really do think that it's a unique challenge that you don't really see in industry otherwise, or even in your studies. Um, Now, to answer your second question, what was the most interesting part about it? I would say it's just the fact that you're handed a hard problem, right? And you have pretty much free reign to try to figure out how to solve it, right? It's it's just problem solving taken to the next level. And what's really nice about it is that you have this huge support network of academics, right? Whether it be your supervisor, the people in your group, your lab, your peers, and even academics from across the world in some cases, especially now with the hybrid online style. So yeah, that's what I feel about research.
Well, I feel like that's one of the things that probably has changed about research in the past, I say few years, but not really a few years, the past maybe few decades, is research shifting from a more individual role to a more collaborative role, more interdisciplinary, which is really something that I think through STEM fellowship, through the Big Data Challenge that you have been trying to promote, which I think is really cool. People working from different disciplines, trying to collaborate to come up with a unified solution to some extent, which is really cool. And I think that's just research in general now, right? Like when I look through a lot of your papers, that's really reflected, working people of different backgrounds, of different areas, right? Just coming together to get a paper published, which is really cool. Make some change. So then I guess one of the questions that I asked yesterday's episode, which I think is a really neat question, what is the one piece of advice you would give to an undergraduate student who is interested in research that is not a cliche answer? to some, like, if you know what I mean, like something that's like unique that you think, you can give them that they might not have heard before.
Yeah, for sure. Well, just to go over the cliches, right? The cliches are get good grades, right, and go to office hours. Um, I do think that the grades are important to sort of stand out to an extent, but I don't want to let that discourage people, right? I think that even if you have like a C average or something that's not like a perfect 4.0, right? Um, I still absolutely think that you can get into a research lab, right? Maybe as a volunteer at first, just to prove your stuff. Um, but anyways, to answer your question more directly, right? The advice that I give to a student that wants to get into an undergraduate student that wants to get into research is the following, right? So one, figure out like what topic you want to really like try out first, right? And don't feel that you're limited to just studying what you're majoring in. So for example, right? Maybe you have like a personal interest in um what's it called? Oh, like a personal interest in like theoretical like comp sci, right? Like just as a passing type thing. But your discipline is in like like biology, like we're I shouldn't say worst case, but very very different from it, right? I've absolutely have seen cases where students like with like, basically no background have been able to get into research labs that were completely unrelated to their discipline, and it's entirely up to them to sort of show their spirit, their moxie, whatever you want to call it, to the professor, right? Being bold and being confident and proving that you don't necessarily not proving that you know the topic per se, but proving that you're willing to learn and that you have a record of completing projects. Like that is the most important thing. Um, Now, in terms of direct advice, right? When you ask a professor, don't be afraid to ask a professor. When you ask a professor to join their lab, right, or ask about opportunities in their lab, you should, I would say, do the following, right? Whether it's a cold email or just going to them in person, you should say like, hey, like, hello, doctor, blah blah blah, like this is my name, um, and I read one of your papers. Make sure you read a couple of their papers beforehand, and come to them with a question about their work, right? And don't feel like and don't feel like your question is stupid, right? People love talking about themselves and their work. Like I'm no exception. Um, so if you come to them with an interest in what they're doing, it'll reflect well on you. And then if you can continue the conversation from there, I think you have a good shot at getting at least a volunteer position.
For sure. Thank you. I think that's some awesome advice. So I'd like to sort of transition a little bit. Let's start off with I guess one of your more digestible papers, like easier to understand for a layperson. And that was the one I was telling you about, the one that you wrote with Pazinski Hong, a comparison of tech sentiment and market sentiment. So first off, I guess if you want to just give like a brief summary of it, that could be really cool. It is a rather short paper, I know, but yeah.
Yeah, sure. So what that paper described, right, is right now people are exploring like machine learning methods and other like fancy types of computations to find triggers or trading like signals in the financial data, right? Which people want to make money, so it's understandable. But you know I think people are way too rash to use these methods without properly understanding them or doing their due diligence and comparing the efficacy of those methods. So what this paper does is it compares um, something called natural language processing and a paradigm under that called sentiment analysis, which basically gives you a measure of how people are feeling or the overall like happiness, sadness, positivity, negativity of a particular set of text data, right? So, this can be like a bunch of tweets. This can be like press releases and paragraphs and books and anything like that. Um, Now, what we did was we calculated text sentiment using the Vader framework, and we compared that and the dynamics of that to something called market sentiment, where basically what we did was we looked at the actual like hard financial data, so the options and futures, volumes and stuff like that, and prices. Um, and we developed sort of a heuristic statistical model where we could classify the market anxiety. So how the traders were betting basically, right? Like, are they betting that the price is going to go up? Is it going to go down? How far out? How far in? Um, and this is really a hard comparison of, just slapping machine learning onto data and just hoping for the best, which is what a lot of people do, and a more, I guess, proper, thorough, like data heavy analysis. And we were able to show that, uh, like that the text sentiment like lagged quite a bit compared to the price movements, right? It would seem that people were only showed their fear or their anxiety once prices moved, right? Like after the fact. Whereas when you
Makes
look at
sense.
like exactly, but whereas when you look at the hard data, right, it was in a lot of cases preceding, right? Which means that, you know, as a researcher, as a trader, as a whatever, you should really do your best to really explore the data and understand what you're looking at, as opposed to just, fancying slapping a fancy algorithm onto it without knowing what it does, basically.
For sure. For sure. That makes sense. So I guess getting into a few specifics. So in the last episode, we talked about sentiment analysis, which is really nice because it kind of ties together a little bit. Um, in terms of the MSM, the market sentiment meter, I know that there are various, I guess, was it, I don't know how you guys described it, moods, feelings, states. I can't remember
Yeah,
how you would
yeah.
describe that.
Sentiment state.
And so, yeah. So in terms of that, the MSM system in general, are you able to sort of describe its function, as well as like potentially how other researchers could use it going forward? Like if someone was interested in, perhaps something other than um, other than the research that like how should I phrase this? Something like where would be some room to build using the MSM, I guess.
Yeah, no, that's a fantastic question, and I will just quickly add that we are doing academic collaborations, meaning we're exploring like avenues of research with various academics. Like, for example, the people that know finance, they might have heard of the Stevens Institute of Technology, where we did um, a a quantum finance project on classification and credit scoring. We did an academic collaboration with currently with the University College London, also on financial matters using the MSM data. Anyways, so for people interested in using this kind of stuff, right? Basically, the market sentiment meter data provides you like a bunch of like financial metrics that you can that we calculate, as well as the sentiment states and our novel mixture distribution, which tells people how exactly people are betting on the price movements. And the avenues of research here really are exploring, in finance, exploring like how you can optimize and improve a trading algorithm, for example. You can probe economic events, like, for example, how the markets reacted to COVID, or any economic event. Uh, you can do things like explore like how like data analysis type things like these compared to like fear and volatility indexes, like the VIX. Um, and a whole bunch of other things. Now, one other thing that you can explore, right, is, the thing that we did, like there are alternatives, right? There are fear and greed indexes too, which basically measure like how scared or how like nervous people are, which is similar to what we're doing with the sentiment meter, with some nuanced differences. And you can explore how exactly you can understand the dynamics of the financial markets using these two things as benchmarks and comparisons. So that's how you would go about it on the finance side.
That makes sense. So then, in terms of, I guess, a question that I would have would be, to what extent is the MSM applicable to other fields, like aside from finance, where like, because generally speaking, the market trends can be reflective of other fields, right? And I think it'd be interesting. I don't know if you have any thoughts on where it could be applied other than finance.
Yeah, sure. So I'm gonna go to a more abstracted viewpoint, right? So
Yep.
so when you look at like financial dynamics, right? Like the financial markets, there is a surprisingly huge amount of overlap with fields like physics, with fields like well, obviously applied mathematics, right? Comp sci, because what people are doing, because they're greedy, right? They want to make money or they want to understand these things, is they try to find like sophisticated ways of dealing with financial markets, right? And you know, interestingly, right, a lot of like statistical physics, statistical mechanics can be directly applied to probing and understanding the financial markets. In fact, a lot of physics PhDs end up after grad school end up going into finance to work in hedge funds like these, so they can apply their math skills and modeling to fields like this. So one really cool sort of translation of these ideas is you can design a quantum field theory, right? A quantum field theory, in order to describe the dynamics of futures markets and bonds and stuff like that. So like something that was designed for the most fundamental of things, right? Like quarks, gluons, like protons, neutrons, electrons, right? Can be applied to people betting on things, which I think is pretty cool. Um,
That's
and of course
insane.
there, yeah, yeah, and of course there are other like fields like fluid dynamics, right? Where you know like people model uh, some like dynamic fluid processes as stochastic, right? And just because of that like fundamental part of their modeling, they're able to port it over to finance and probe that way. So I don't know. I think there's a lot of overlap in the methods and how you could apply one thing to another.
So I'd like to run with that stochastic view, and sort of pivot a little bit to, I guess, your thesis, to some extent. So you wrote your thesis. Also, just for the viewers, all the documents, all the papers we're talking about, I'll link them in the description, just so that if you want to read them, they're all there. And also, Anish, I'll link your contact info if you want, like your LinkedIn or whatever.
Sounds good.
So yeah, so in terms of your thesis titled "Quantum Monte Carlo Methods and its Application to Fermi Liquid Theory." So I guess as you read through, the abstract, the introduction. I think the introduction was written really well, by the way. I really enjoyed that. That was a fun read, especially as someone who's like not a physics major. But I guess so. My questions would be for a lay person, what? But why don't we start off with I guess the two main questions, if you want to answer the titular question, are what is quantum Monte Carlo methods, or what are quantum Monte Carlo methods, and what is Fermi liquid theory? If you want to go into those a little bit, and then perhaps we can have a better groundwork to start moving forward through it.
Yeah, sure. Okay. So first, Fermi liquid theory, right? So the idea here, right, is that you had a okay. So there was a guy back in the day named Enrico Fermi, right? He's an Italian, I believe, physicist. Uh, yeah, that's right. Sorry, Italian physicist, right? He described some quantum particles that have some spin of a half, right? Which is just a property basically. And he was able to describe these particles using like fancy quantum mechanical methods and really get exciting results because before this, like quantum, it didn't mean anything before like the 1900s, and some really smart people were able to understand that these wacky properties just using some interesting assumptions. Um, so then, sometime later, a very, 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 very smart man named named Landau, a Russian physicist, uh, he he was like, oh, like this is kind of cool. But I realized that the calculations to understand these fundamental particles as you add more and more of them gets super hard. Um, what if I just think about it a little bit and create a whole new framework uh, to make it a lot more tractable and easy? And this mad lad, what he did was he sat down in his chair and he's like, oh, this is obvious how you can make this easier. So then he wrote it down in a paper and he was like, this is how you do it. Um, and then and then like 10 years after the fact, right, like a bunch of other smart people spent a bunch of time trying to prove him, either right or wrong. And after some time and a lot of people later, they were like, wow, he was right, and he just figured that out while sitting in his armchair. This is ridiculous. He's too smart. Um so then,
That's
the
awesome.
framework was, yeah. So the framework was laid out how to apply this to electrons. And interestingly, we required a lot more computational sophistication and power in order to apply these to more relevant systems. And this is where the quantum Monte Carlo thing comes in. So the quantum Monte Carlo method is a way to sort of address, right, um, address the case when you have like a bunch of these quantum particles interacting with each other, which otherwise is very, very hard to do. And this algorithm makes it so that you can get really accurate, really precise answers in a short, quote unquote, amount of time. Um, so the idea behind this work was to see if you could apply Fermi liquid theory to infinite neutron matter, so a ton of neutrons, um, within the Fermi liquid theory framework, because it was designed for electrons, but you know, potentially you should be able to apply to neutrons as well and understand the properties of things like neutron stars and things that we can't like touch or probe here on Earth.
Mhm. So, so quantum Monte Carlo methods. If you want to like, I mean, I know this might get a little more technical, and that's okay, because I think we've laid the groundwork a little bit. But what are some of the technicalities of the methodology that you designed, or I guess propose? And so, yeah, I guess if you just want to take us through that, that could be kind of cool.
Yeah, sure. So with the okay, so with the quantum Monte Carlo stuff, right? Basically, you have like your Schrodinger equation, right? So the equation that tells you all of the 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 dynamics and fundamentals of quantum particles, right? Um, and the problem with this thing is that it gets really, really hard when you add more and more particles to it, right? Because you get a bunch of different terms and a bunch of terms that are like impossible to solve analytically and just super duper hard to solve computationally. So what you have to do instead is apply these approximations. The problem with approximations is that they're approximate, and if you have a bad assumption, then everything that you do is going to be like non-physical or wrong. So
Well,
one,
especially when you're like, I mean, correct me if I'm wrong, but especially with approximations, when you're looking at things that are as small as, say, atomic particles, subatomic particles, right? You're really you come up with the issue of you have such a small margin of error, For sure, I agree. So I guess my last question on this paper, and then we can move on a little bit, is where if you were to if you were given, you know, funding, opportunity, time, everything to resources to do this, like an extension of this paper of your thesis, where would you go? Like what I guess, you know, most papers have future areas of research. What future area of research would you be interested in pursuing? Where would you go from here?
So me personally, or someone that wanted to continue this work?
You personally.
Okay. So
Let's do that.
I'll sure. I'll answer both because I can do them quickly. So where someone that
Sure.
wanted to continue that work would go is they would, well, I guess my reckoning is they would try to rework and add to the framework such that you can account for the electromagnetic interaction, because then you could add protons into it, which would, you know, repel each other, and that would affect potentially the dynamics of things. And then you could start to probe
Mhm.
things like heavy nuclei, or even neutron stars that are proton dense, basically. Um, Now, where I would, like, where I am going right now with my own research is I found that that a lot of the methods that I was using, you know, just throughout my whole physics career, right, um, involved a lot of like data science methods, as well as like um, understanding of stochastic systems, right, like statistical systems, random systems, you could call it. And I found that, you know, the thing with physics, or at least nuclear physics, is that all you sometimes you have to wait like a decade or more to sort of experimentally verify your theoretical results, which, you know, is a long time, right? And, you know, just
Mhm.
as an example, when it came to the Higgs boson, right? Um, like the guy behind it, he came up with a theory back in like the 80s or 90s, right? And that wasn't verified until like 2010 or something like that. So that's like 20, 30 years waiting to verify that, which is, you know, uh, quite hard to I guess deal with. And for me, I wanted to be able to apply like that, like those tools and those techniques, right, um, to something that I could sort of verify more readily. And for me, I was happy to discover that there was quite a happy marriage between physics and the financial markets, right? I was able to take all of the methods that I was doing like in physics, like just like almost literally all, like most of the methods that I was using in physics, and directly apply them to the financial markets and have like this sort of like almost instant verification, right? Because there's so much data that's like live and like from like historical, that you could like test your theory on and be like, oh my god, it worked, or like, oh my god, it didn't work. Let's think about it some more. So that's where I decided to take it. And I'm sorry, and just to quickly add on to that, um,
Mhm.
like because of my deep interest in physics, like I was able to like explore the idea of like combining quantum computers of all things, right, with finance, right, applying like something else in a different field of physics research, right, to something that was like completely out of my domain of expertise at the time. So, or when I first started, which was really cool, and I think physics was the thing that opened up the path for me to be able to do that.
That's awesome. Thank you. So moving on to your other, I guess, I feel like from what I read, it appears that you have, I would suggest, two major papers, your thesis and then this one. Is that a fair thing to say?
So when you say this one, you're referring to my my undergraduate one, right? The 2017 paper.
Yeah, with Dr. Strosta.
Yeah, I'd argue. So, you know, truly, I think out of my all my physics stuff, my the 2017 one was probably my personal favorite, just because it was, I don't know,
Mhm.
it was like a pretty cool like marriage between the theory and the experiment. Um, so you know, before I continue, I'll let you ask your question.
Sure. So just so for the viewers, the title of this paper is Collective and Single Particle Degrees of Freedom in Rotating Nuclei. So this was written with Anish and Dr. Krzysztof Starosta. I'll again put a link in the description for that. So in terms of, I guess generally speaking, it sounded like you had some interesting thoughts. If you want to, take, it's a dense paper. If you want to take some time and just walk through the thought process and just a general, I guess, summation of the paper, that would be useful.
Sure. Okay. So atoms are made up of these things called nuclei, right? And you're taught in high school and even early undergraduate, right? That honestly, like most of undergraduate, that excuse me, nuclei are these perfect tiny spheres, dots, right? It turns out that that's not really true, right? um like nuclei can take on all sorts of these mathematical shapes, right? They can be uh like described as spheres, ellipsoids, like football shapes, right? Like gourds, like octopoles, and so on and so forth. And you know, because of that, right, the theories that you apply and develop sort of have to, I guess, to be accurate for certain regions of the nuclear chart, is you have to account for these things. And one of the most common deformed nuclear shapes is like that football shape, the ellipsoid. So what you do then is you go okay, well, how can I incorporate this into my calculations? And there are a whole bunch of different ways, right? One popular way is called the rotor model, where you basically you take the nucleus as sort of a mean field, and then you so it, like an like a fancy average basically, and you describe it as that football shape, and then you look at the dynamics of that football shape with some quantum like like specifications applied to it. And really interestingly, right, is that in some nuclei that fit this football shape, right, uh, it matches really well the theoretical calculations that you get, right, almost perfectly. You can see examples of this if you just look up rotor model or ellipsoidal nuclei, right? Um, so that's one thing. But you know, not every ellipsoidal nucleus can be described perfectly by just averaging things out, right? Like there are bulk properties of the nucleus, as well as these single particle like properties that can really affect the interactions and things. So in order to encapsulate both the bulk properties and the single particle degrees of freedom, you want to try to combine the two somehow, and that's what we did in this paper. So we we um we took a rotor, right, like that bulk average, but we added the nuance to it, where we take two particles out of that bulk and treat them as their own individual things. Um, and then we made it so that those two things could hit each other, right, interact with each other through what's called a delta force, and and see what the model showed and whether or not this was a good description and a good predictor of certain nuclei and their properties. And we were able to show that that this indeed, for a bunch of different nuclei, is pretty good at replicating the results. And because this is a model that we can function, pardon me, this is a model that we can calculate as a function of nuclear spin. It means that we can predict properties of the nucleus. We can predict energy, we can predict G factor, we can predict a whole bunch of things, and quadrupole moment. And that's the paper. We made this model. We show that it can be applied to a bunch of different nuclei, and we can predict the properties of nuclei to be verified by experiments.
So just a question that comes to my mind, because I mean, like I said, I come from a more, I guess, abstract, or I guess pure mathematical side of things. Or I guess going into pure mathematical. I haven't started yet, but thinking a lot deeply about those sorts of topics. And my question, the thing that comes to mind now, I am familiar with the whole notion that, nuclei aren't just dots, right, in space. They're like, not only are they shaped, but they're also, or to some extent average shaped, but they're also moving, right, which has a lot of, anyone who's ever done like mechanics, physics mechanics is like, how complicated that can be, right? So I think that yeah, I think that, like, generally speaking, it makes sense. But also, what's interesting to me is that the fact that nuclei aren't symmetrical perfectly to some extent, right? The fact that they aren't, like, you would imagine, right? You would imagine to the extent that things on the large scale in our universe tend to be fairly symmetric, at least to my understanding. When you visualize, at least they tend to be fairly symmetric. It's interesting that at the small scale they aren't, and I don't know if you have any thoughts on that, or any how that notion connects to what we were talking about. But I'd love to hear what your thoughts are.
Yeah, sure. So symmetry is an interesting thing, right? Like on okay, so even in like a macro scale, right? The things that you and I can see, I'd argue that that just about nothing is perfectly symmetric, right? Like if you look at like the smoothest like metal ball, I don't know, or it's like a glass sphere, right? Even that isn't like perfectly symmetrical, because if you look at like the smaller, like, I guess, shape of it, right? You'll always find like cracks or little divots or things like that, right? Which breaks the symmetry of things. Um, and on the quantum side of things, right, like the most fundamental side of things, you can have like electrons, right? Like these fundamental things, like you can describe them as particles and waves, and you could argue that those have like a spatial symmetry to them, right? Um, but the interesting thing is that like symmetry in like 3D, it means like spatial symmetry, right? Like I don't have anything spherical on me actually, which is kind of funny. But like you can take a ball, right? And then you're like, okay, that's symmetric, right? Because like if I split down the half and mirror it, right, or if I rotate it, it looks the same, right? Um, but when you get to the quantum level of things, right, like spatial, like it means something different, right? Because like these things at this really tiny level can be described as particles and waves. And what that means is that they don't have like necessarily a really defined shape, right? They have they have a probabilistic shape, which is another like can of worms to open up, which is really cool actually. But uh, you know, what I want to say is that at the quantum level, like symmetry does mean something different, right? Like you can have spatial symmetries, you can have like time reversal symmetries, you can have well, like I'm spacing out here, but like you can have a bunch of other symmetries too, and the symmetry breaking is the actual interesting thing, right? Because like at the quantum level, if you had like you can have like spatial symmetry, right? Like if I rotate an electron, it's still an electron, right? It looks quote unquote identical. Like no matter how you calculate it, it looks identical. But when you have like these like for example like the ellipsoidal nuclei that I described about, right? If I rotate it, right? Like it like if I rotate it along the long axis, sure, it might look the same. But if I do this, right, if I rotate it like that, obviously I can see
Yeah.
it change, right? And that's reflected in a bunch of its quantum properties, and and you can find like symmetry breaking in those properties, deviations from what you expect from the norm, and that tells you about the fundamental nature of whatever you're looking at. So symmetry breaking is actually really cool, and the interesting thing I'd argue within the quantum, I guess, domain.
Yeah, I definitely agree. I think symmetry is just like so fascinating. Breaking of symmetry is so fascinating.
Mhm.
Like, you see it everywhere, right? In so many fields. But um, I guess perhaps one thing that would, like, We'll do one more on this paper. So, what is the I don't want to mispronounce it, Jan Teller effect?
Oh yeah, sure. So
And
the Jan.
if you were to describe that to like, if you were able to describe that to a someone at an undergraduate level, or someone who's taken a few chemistry classes or a few physics classes, right? That kind of stuff.
Sure. So the Jan Teller effect, which honestly I might have been pronouncing wrong for all these years. Um, it's it's the description of why you have like spontaneous symmetry breaking in molecules like chemistry, and what does that mean, right? Well, interestingly, right, like molecules aren't perfectly symmetric either, right? Like sometimes you can expect them to look like a pyramid shape, right? But you'll notice that like when you actually look at the structure of the molecule like, through experiments, you're like, huh, this is weird. This isn't like perfectly symmetric. These bonds are shorter than that one for like no apparent reason. And Jan Jan and Teller, they were able to be like, well, you know, really, right? If we look at this from a physical perspective, we know that nature wants to be in the most energetically favorable position, right? Like that's just how nature works, right? You want to be at the lowest energy, the most stable, or what have you. Um, and reality will I shouldn't say bend to this, but reality will make it such that like you can do wacky things in order to get to the most like um energetically like stable or lowest energy like state. And one of the ways of doing this is like literally just like changing the shape of molecules, right? Like the molecule knows is the wrong word. Like the molecule's like I want to be like calm. I want to be in the lowest possible energy. I'm just gonna stretch out until I can do that. Um, so it does that spontaneously, and this is really apparent and really important thing in inorganic chemistry and organic chemistry, honestly, which for sure if you study chemistry you'll encounter. Um, so that's what the Jan Teller effect was, and the idea was to apply that concept of spontaneous symmetry breaking to nuclei. And in the paper, we see that after modeling and stuff like that, we see the we see we see the symmetry breaking and this change in the properties of the nucleus as you like go higher and higher in spin. You have pair breaking, or what some call backbending. A bunch of different terms for it.
Makes sense. So then I guess let's pivot, because there's a lot in that paper and folks can read it if they're interested. So I guess one question that I have for you, just to kind of start wrapping things up here, um, what's what was the most interesting result you've ever had from any of your research? Like, what was something that whether you did the calculations, did the analysis, and you were like, huh, that's not what I expected. Have you encountered that? And I'd
Uh,
love to hear about it.
yeah, sure. So it's happened a bunch of times, right? And I say that like not to brag because it's gonna elaborate a bit, right? I've seen that a ton because I was wrong, right? I calculated something wrong, and I was like, that doesn't make sense. And then I was like, of course it doesn't make sense. I messed up the calculation somewhere. Um, like one like one example of that like just like destroyed me at the time. So what happened was like I was spending like 2 weeks on trying to make something work, right? And I finally got the I thought like the math to work and the code to run, and I was like, oh my god, this is exciting. Let's see what it plots, right? And oh, sorry, I just gotta plug in my laptop quickly. Um,
No problem.
sorry. Okay, perfect. Right, right. And when I plotted it, right, I expected like, or what I wanted was like the plot to look like straight line and then up like that, right? Like straight line diagonal.
Mhm.
And what ended up happening was I got straight line, right? And then it was like bam, like downwards. And I was like, okay, either this means that like that I've I've discovered like a fundamental break in physics and I'm about to win the Nobel Prize, or I made a mistake in my math, right? And oftentimes when doing research, right, you're gonna come across like a lot of moments like these where you make a mistake and you get like this thing that just doesn't make sense, and you learn to sort of sanity check. Uh, Now, in terms of results that like were interesting, is actually in that 2017 paper, right? So um,
Mm.
we described the symmetry breaking through this model, right? And we found that for certain nuclei, right, for certain configurations, that like that there is a really interesting and apparent like dynamics of the G factor, and the G factor is basically like a thing that you can measure that quantifies like like the rotation in an electromagnetic field of a particle, right? Like that's I think the simplest way to like abstract or just describe it. And it was basically just like it was like not doing anything until you reached like a dynamic enough like part of the of the a fast enough rotation basically for the nucleus, and then all of a sudden it just like shot up and then it started to like trend back downwards. And what this meant was that there was like a really like an interesting like way of measuring this and sort of verifying things that we were doing and understanding the properties of the nucleus like through experiment. um and it hasn't like experimentally like just because of where the hardware is right now, it hasn't been possible to measure. But once it is possible to measure, you should see that. And this super simple like model that anyone can use effectively, right, is able to describe that. And if we are able to verify that, it has like a lot of, I guess, good implications for how you can probe like nuclei within this specific region.
That makes sense. So I guess yeah, we can wrap up. So do you have any other final thoughts that you would want to share with anyone? Any
Yeah, sure.
tips or any yeah, go ahead.
Sure. So so tips for like high school students, right, is and undergrads or wherever you are in your career is like do not be afraid of sounding stupid or feeling like you're not good enough to pursue something. Like if you have confidence and you have like, even the slightest bit of motivation, right, you can do amazing things, right? The only difference between, I guess, like you and the person that you look up to, right, is that they like mustered up the courage to take that first step, right? And I think that now is probably the best time thus far in history to be able to learn and do research, right? So I implore you to just try doing something that that's slightly out of your comfort zone, um, because you can and will do great things.
Awesome. That was very well put.
Thank
Well,
you.
thanks for joining me today, Anish. And thanks everyone for watching. That was a really awesome conversation. Definitely exceeded my expectations. So thank you.
Thank you so
Awesome.
much.